Welcome to Lecture 13, which is on Fermat's Little Theorem, as well as polynomials and congruence. We've talked a fair amount about how to solve congruence modulo n in various different contexts and situations, mostly linear congruences or systems of linear congruences. But I think there's one little thing that kind of slipped through the cracks in our previous work, which is this, or at least at a very minimum I underemphasized it. So if we have n, which is the product of prime powers, right, so that's the prime power factorization of n, then for a and b integers, a is congruent to b mod n, if and only if a is congruent to b mod each of the prime power factors composing n. Okay, and so the proof is essentially just to apply the Chinese remainder theorem. All right, because the set of coprime moduli of the prime powers, we can solve all of those. Well, remember that the simultaneous solution of all of those is a solution mod the product of all those, which is just n here by construction, and so that's essentially it. So just to give you a couple of examples, like if I had a congruent to b mod 50, to decide whether or not that was the case, I could see if a was congruent to b mod 2 and if a was congruent to b mod 25, because 2 and 25 are the prime power factors of 50, right? 25 is 5 squared, of course. Or if I had a congruent to b mod 588, well, 588 is 3 times 4 times 49, which has got, so you got your 2 squared, you got your 3, you got your 7 squared. So you could check a congruent to b mod 4, mod 49, mod 3. If you had all three of those, you get the 588. All right, and vice versa. So there's something we haven't really, I don't think we'd use that much, but it's there. So that's the first thing. So next up here, let's talk about congruence and polynomials. All right, so I'll start with a couple of examples. So these examples kind of give you some perhaps surprising things. Like if you're looking at, x squared minus 1 congruent to 0 mod 8, that's equivalent to looking at, so here's something I'm using in this first example is this let me say remark. We can either look at x squared minus 1 congruent to 0 mod 8, right? Or we can look at x squared minus 1 equals to 0 in Z8. These are two different ways of looking at the same problem. I suppose to be fussy, maybe I shouldn't use the same letter x for both, but I will. All right. So you're like, well, you say you're looking at congruence in polynomials, but now you're talking about x squared minus 1 in Z8. Well, it's a different way to look at it, right? It's the same thing. Now, it's a polynomial, so we can plug in the different possible zeros for Z8, which are what, 0, 1, 2, 3, 4, 5, 6, 7, with bars on them, because it's Z8, right? And, see, this is the thing, guys, is I get tired of writing the bar over things at times. So, in fact, probably past this lecture, I'm going to stop drawing the bars. But, all right, anyway, so as you can check out, f of 1 bar, 3 bar, 5 bar, 7 bar, these all work out to 0, whereas the evens in Z8 all are non-zero. But this is actually kind of a little bit disturbing because we have a quadratic with 4 distinct zeros. But I thought a quadratic equation only has 2 solutions, right? Well, that's not the case over Z8. So, and in fact, you can see that this also extends, this weirdness extends to how we can factor. So you can either factor x squared minus 1 as x plus 1 times x minus 1, right? Or you could factor it as x minus 3 times x minus 5, because when you work that out, you see you get that minus 3 minus 5, which is 8, which is 0. So you get, again, x squared, and 15 is minus 1 mod 8. So this and that are two different factorizations of f of x. So you don't have unique factorization of polynomials either over z8. So if we're working over z8, the way we solve polynomial equations, or the way we solve congruences, mod 8, it's a little bit different than our familiar experience over, say, the field of real numbers or complex numbers, okay? So that's a little bit surprising. 4 solutions for a second order problem. Another surprise, we could have this congruence, right? Nx to the d plus n times n minus 1 x squared plus n congruent to 0 mod n. Well, the thing is, on the left-hand side, all of that is actually congruent to 0, independent of x. So the solutions are all the way 0 through n. All n congruence classes are solutions to this congruence, right? So that's a d-order problem with n solutions, and so that's a little bit odd. And the other thing is, you could have a quadratic which doesn't appear to be a repeated root, but it actually is. So like x squared plus 1 in z2 has 0, not a solution, 1 a solution, and that's because x squared plus 1 is actually the same as x squared minus 2x plus 1, because 2 is congruent to 0 mod 2, and so this is really x squared plus 1 is x minus 1 squared mod 2. So all of these, I think, are a little bit surprising if we compare them to the usual story of equality, right? But all of that said, there is some things which are pretty familiar. And so here's one. Lagranges Theorem on Polynomial Congruence. Let P be a prime, and so some of the troubles with my previous examples were working mod 8. Of course, 8's not a prime, right? And the other problem, like in the middle example, was that all of the coefficients were congruent to n, which was also a problem, right? So this avoids both of those pitfalls. We were working mod a prime, and we're assuming that all of the coefficients, right, all the coefficients here, they're not all congruent to 0 mod p, okay? At least some of them, at least one of them is not congruent to 0 mod p. Anyway, if that's the case, then f of x is congruent to 0 mod p for at most d solutions mod p, right? So you have at most d congruence classes, which solve this d-th order congruence. Well, I don't know that this is a d-th order congruence. I would say that this is a d-th order congruence if a sub d was not congruent to 0, right? So I would say the order of the congruence is for this kind of thing. Excuse me. I need to get some candy or something. Just a second here. Oh, man. Forgive me, I'm going to chew some gum. Let's see here. So here's the proof. And so I'm following Jones and Jones, pages 66 to 67 of their elementary number theory book, which has largely inspired these lectures. All right, but I did intend for these lectures to stand independent of that book, so they do, I think. Anyway, so it's by induction on D. First of all, for D equal to 0, if a sub 0 is not congruent to 0, then it has no solutions, which is the theorem. All right, because it has less than or equal to 0 solutions. Suppose inductively that all polynomials of degree d minus 1 or less or lower have at most d minus 1 solutions mod p. Consider f of x equals to a to the d, a sub d x to the d, da 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 plus ax, a1x plus a naught. All right, where of course not all of those are congruent to 0 mod p, the coefficients, right? So if f of x is congruent to 0, has no solutions, then we're done, right? Because that would be less than d solutions. However, if there exists an a for which f of a is congruent to 0 mod p, that means that p divides f of a, right? So let's calculate. So this is kind of a neat calculation. So f of x minus f of a, right, where that f of a is the a that is this one right here, gives you a sub I to the xi minus a sub I to the ai. I think if I had to do it over again, I would have used a different letter for the coefficients of f of x here, because that looks funny. But anyway, it is what it is. So we can factor the a sub I out of both of these and group the sums like that. And then you notice that at I equals to 0, we get 1 minus 1, which is just 0. So we can start the sum not from 0, but from 1 without losing anything. We just lost 0, which is fine. And so we have a sub I x to the I minus a sub a to the I. But you might notice that this right here, for I greater than or equal to 1, we can factor out x minus a by this straightforward polynomial identity. You can just multiply this out to see it's true, right? This times that gives you x sub I. That times that gives you minus a to the I. But everything else cancels, because you get like a minus a x to the I minus 1, but then you got a plus a x to the I minus 1, right? So this times this cancels that times that. And there's that kind of cancellation for everything else between this term and that term. So what you get then, putting this all together, so you have that at each I. So you plug this identity up in here, and then there's an x minus a on everything, so you just factor it out, and everything else goes together to make this g of x. All right, so there is a little bit of a gap here, but it's a pretty straightforward one if you think about it. Now, g of x then has degree d minus 1 at most, right? I mean, it could be that some of these things were 0, so you could end up with like g of x lower degree, if f of x and if f of x wasn't actually d degree, you know. But anyway, so the degree of the g of x factor is at most d minus 1. Okay, so then what? Let me scooch this up a bit here. So then we have f of x is f of a plus x minus a times g of x, and notice that p does not divide all the coefficients of g of x, because if it did, then p would divide all the coefficients of f of x, which contradicts what we assumed. So that means some of the coefficients of g of x must be not congruent to 0 mod p. So by the induction hypothesis, g of x is congruent to 0 mod p, has no more than d minus 1 solutions. So if we go back to the original congruence, if we suppose that we have f of b congruent to 0 mod p, then that gives us, by the identity we worked out, f of b minus f of a equals to b minus a g of b. But f of b minus f of a is congruent to 0 mod p, therefore p divides b minus a times g of b. But if p divides b minus a times g of b, that means either b minus a is congruent to 0, or g of b is congruent to 0 mod p, which means we can we either have, so counting everything, we've got 1 or up to d minus 1 solutions. So add those together, you got d solutions at most, which is the theorem. So there you go, proof by induction. So that's the Lagranges theorem on polynomial congruence. There are some corollaries here. Here's one. Let f of x be a to the d x to the d plus da 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 da, and let p be prime. If f of x has more than d roots in z mod p, then p divides a sub I for each coefficient, right? So straightforward. If you have more than d roots, it must be the case that not all of the not any of the coefficients are non-zero mod p. They have to all be congruent to 0 mod p, otherwise you would contradict the theorem we just proved. So that's nice. So here's an example. F of x equal to 13x has 13 solutions in Z13. 13, I should say, roots, solutions, let me be clear, of f of x equals to 0. I mean, that's what we're talking about, right? F of x equals to 20x cubed plus 40x squared plus 20 has 20 solutions in Z20, right? Despite the fact that it's a, curses of f of x equals to 0. There we go. Equivalently, you could say, 13x congruent to 0 mod 13, or you could look at 20x cubed plus 40x squared plus 20 congruent to 0 mod 20, right? And these would have more than more than 3 solutions, more than one solution mod 13. Now 20, I guess to be fussy, 20 is not a prime, so this doesn't this isn't a direct application of that, right? But if you go back to the first theorem we had in this lecture, 20 is what? It's 2 times 2 times 5, right? So it is the case that 20 dividing each one of the coefficients means, by the way, that 2 divides each of the coefficients. Well, 2 squared divides each of the coefficients, right? And 5 divides each of the coefficients. So you can apply the corollary to Lagranges theorem, mod 4 and mod 5, and hence you get this mod 20, because we can go between congruence mod n and congruence mod, simultaneous congruence mod all of the prime power factors of n. So we actually have to use the first theorem in this lecture to make the connection here with this number 20 example. All right. Anyway, the example above is rather silly if we view everything from the vantage point of Zn, because really these are just the zero polynomial, right? I mean, this is the zero. This is the zero polynomial because 13 is 0, 20, 40, and 20 is 0 in Z20. So really we're just saying f of x identically equal to 0 has 13 solutions in Z13, because that's all you have, 13 things. And f of x identically equal to 0 in Z20 has 20 solutions, because there's 20 things in Z20. So, I don't know. I think if you look at things from the perspective of Zn, these statements are not terribly impressive. If you look at them from the perspective of congruence mod n, it seems like we're saying something, but anyway. So, now we come to Fermat's little theorem, which is not directly something related to what we just did, okay? So there's a little bit of a, I don't have a good segue here. It's not, it's related, it's about congruence, right? But it's not, I'm not saying that this is somehow built off Lagrange's theorem directly, okay? Anyway, here it is. If P is a prime and A is not congruent to 0 mod P, then a to the power p minus 1 is congruent to 1 mod p. All right. So I'll tell you about 2 proofs of this. And the first proof will be quote-unquote number theoretic. So here it is. So if you look at 1, 2, all the way out to p minus 1, right, these are a complete list of the non-zero members of ZP, right? The other one that's missing is p bar, which is 0 bar, right? So that's missing. But these are all the non-zero members of ZP, but you notice that we can multiply these by a not equal to 0, right? And we get another list of distinct members of the congruence. Now, why is that? Why are they distinct? Why are these distinct? Because if we had a bar x equal to a, if we had ax bar equal to ay bar, notice that a inverse bar exists. How do I know that a inverse bar exists? Well, if a bar is not equal to 0, that means the GCD, right? The GCD of a and p is equal to 1 for a bar not equal to 0, right? Which means that a bar inverse exists, given our previous discussion, right? So we know that any non-zero member of Z mod P has a multiplicative inverse, and as such, this list has to be distinct, because if you had 2 were equal for x and y not equal, then that would give you x and y are equal. Anyway, so it's a distinct list, okay? So what that means then is if you multiply 1 through p minus 1, it's the same as multiplying a through p minus 1 times a, like that, right? But then, by algebra, this is p minus 1 factorial, and you can just factor out the a, and you got a to the p minus 1 equals to times p minus 1 factorial. But then, as p minus 1 factorial is co-prime to p, we know that p minus 1 bar inverse exists in ZP, hence multiplying the above by p by the inverse of that, we get 1 is equal to a to the p minus 1, in terms of ZP, which then, translating back into congruence, gives us that a to the p minus 1 is congruent to 1 mod p. So there you have it. This is Fermat's little theorem. Now the other way to prove Fermat's little theorem, so we'll look at examples of this towards the end of the lecture, okay? Don't worry, I do have examples, just not here, not quite yet. So the other way to prove Fermat's little theorem is, hey, come on. I'm having trouble here with my papers. The other way to prove Fermat's little theorem is with group theory, although I'd say that in some sense that proof I just showed you had a little bit of group theory in it also. But what can I tell you? Group theory is everywhere. So the other way involves a result from group theory, let's say that. And so just to remind you or introduce you to, I hope I'm not introducing you. If I'm reminding you, that's better, but if not, I hope this is self-contained anyway. What is a group? A group is a set with a binary operation which has an identity, is closed under inverses, and is associative, right? The order of an element in the group is the smallest positive integer for which x to the n is equal to the identity. If you're using a multiplicative notation, sometimes this e would be equal to 1, right? Sometimes we say e equals to 1 for a multiplicative group. If it's an additive group, if you're using addition for your group operation, then if you add x to itself n times, which you could say nx, is equal to 0, so that's additive group order versus multiplicative group order. So the identity is 0 in an additive group. So just here's an example, rather than more blathering about the definition. U10 is a multiplicative group. It's closed under multiplication. The numbers in U10, these are the numbers in Z10, which are relatively prime, with representatives relatively prime to 10, namely 1, 3, 7, and 9. And you can calculate 3 squared is 9, 3 to the cubed is 27, 3 to the fourth is 81, which is 1 bar. And so the order of 3 bar is 4. In contrast, 9 squared is 81, which is 1 in Z10. So the order of 9 is 2. The order of the identity is always 1. And the order of 7 is also 4. Okay, so here's some examples of multiplicative order. All right. Now, in contrast, if we were to talk about order in, say, Z4, which is an additive group, it's closed under addition, right? Then here, you've got 1 plus 1 plus 1 is 3, which is not 0, but 1 plus 1 plus 1 plus 1, 4 times, right? So that's 4 times 1 bar. Well, that is equal to 0 mod 4, so the order of 1 is 4. Also in Z4, the order of 2, since 2 plus 2 is 0 mod 4, you've got the order of 2 is 2. Okay, so there's the difference between additive versus multiplicative order. It's the same idea, but sometimes we have additive groups, sometimes we have multiplicative groups. We're interested in both in here. I think mostly in the future lectures we're talking about the multiplicative group of UN, but we will look at how that can be analyzed in terms of Z mod n. So Z mod n is an additive group, but the multiplicative part of it, so Zn is actually a ring, right? Which means it has an addition and a multiplication. So it turns out the single ring of Zn has both an additive group, which is interesting, the Z mod n, let's say, as well as the multiplicative group, which is interesting, which is the group of units, which we call UN, right? They're both there under the same system of arithmetic, namely modular arithmetic. Anyway, so here's a theorem from group theory. In a finite group, all right, if you have a group of order n, then we have x to the n is equal to e, or nx equal to 0 for every x in the group. So the order of the group being n, that means the number of elements in the group is n. Now, I thought I could just scribble out a short little proof of this, but as I started to look at it, I was like, oh, and then I need to know that, and then, oh, I need to know that, and oh, I need to know that. And I mean, the proof of this is very short when you get to it in group theory, but the road leading to it has many chapters, okay? So I decided not to include a proof here. At previous time I taught number theory, to make this careful, I found myself adding a 70-page supplement to the course. So don't want to beset you with that. So I'll just tell you this, the proper proof requires a kind of big detour, but this is something you would have learned, surely you would have learned in group theory if you took a course in group theory. The order of any element in a group of finite order is at most the order of the group. And in fact, the order of any element has to divide the order of the group more generally. That's a consequence of the fact if you take an element, you can look at the subgroup, the cyclic subgroup generated by the element, that has to give it a subgroup of the group, and then by Lagrange's theorem, that has to divide the order of the group. So I'm starting to talk through some of the parts of the detour, so let me stop. So here's an example. If you look at, if you look at my previous examples, x in U10 has x to the fourth equal to 1 for every x, and x in Z4 has 4 times x equal to 0 for every choice of x. These are both true. You can go back and look at my example 7 and example 8 and see it's true, right? I mean, obviously 3 and 7 to the fourth are 1, we proved that, but you know, we had 9 squared is 1, so if 9 squared is 1, of course 9 to the fourth is 1, and of course 1 to the fourth is 1, so everything to the fourth is 1 in this group of order 4. And notice that the order of 9 was 2, and 2 divides 4, like I was saying. And the same story bears out in Z4. So, all right. All of that said, there's your short walk down memory lane there for group theory. And here's the proof of Fermat's little theorem from group theory. Let's see here. So if A is congruent to 0, not congruent to 0 mod P, right? That means that A bar is not equal to 0 in ZP, which means that A bar is a unit. So A bar is an element of the group of units, which has P minus 1 elements, right? Because everything is co-prime to P if P is prime, right, except for P itself, or 0 itself, if you want to look at it that way. Thus, A to the power, A bar to the P minus 1 is equal to 1 bar, which means that A to the P minus 1 bar is equal to 1 bar, which means that A to the P minus 1 is congruent to 1 mod P. And there you have it. That's Fermat's little theorem. I'm using the abbreviation FLT, which is a little bit dangerous. I think most people, if they see FLT, they're thinking Fermat's last theorem. But that is the last theorem of Fermat we will discuss in this course, so it'll be a while before we get back to FLT. Needless to say, this is a much more, well, it's funny, this is a probably an easier theorem to state to the uninitiated, but it's much harder to prove. In fact, we will not prove Fermat's last theorem in this course. I'll just talk about its proof. Anyway, so Fermat's little theorem here. And corollary, A to the P congruent to A mod P for all A. In other words, x to the P is equal to x for all x in ZP. That's very interesting. That means we can reduce polynomials of higher order, right? If you have if you're working mod, let's say 7, and you have x to the 8th, well, you can say, well, x to the 8th, rather x to the 7th is just equal to x, you know? That's kind of weird. We'll put this into practice here in a future example. But the proof is very simple, A congruent to 0 mod P, then A to the P is congruent to A, right? And if a is not congruent to 0, then a to the p minus 1 is congruent to 1 by the Fermat's little theorem, which then multiplying, which of course then gives us this equation in ZP, which multiplying by a gives me a to the p equal to a in ZP, which gives me a to the p congruent to a mod p, right? So whether a is 0 or not, you have x to the p equals to x in ZP, which is to say a to the p is congruent to a mod p for all a. So there it is. And then there, now this corollary is it a corollary? I know calling this a corollary is a bit of a stretch. I think it's really more of a theorem. But an integer n is prime if and only if n minus 1 factorial is congruent to minus 1 mod n. This is called Wilson's theorem, but Jones and Jones mentions that it was proved by Lagrange in 1770. So anyway, if p is equal to 2, then the theorem is true. All right. 2 minus 1 is 1 factorial. 1 factorial is 1, which is congruent to minus 1 mod 2. If p is an odd prime, okay, then we're going to look at this polynomial. F of x is 1 minus x times 2 minus x, p minus 1 minus x plus 1 minus x to the p minus 1. All right. And so this is an interesting polynomial because if you look at it, the x to the p minus 1 cancels because when you multiply these out, you get a minus 1 to the p minus 1 because there's p minus 1 factors. So you got that minus x, minus x, minus x, p minus 1 times. So that gives you a minus 1, p to the minus 1 times x to the p minus 1. But since p is odd, p minus 1 is even, which makes this factor just be 1. And so that just gives you x to the p minus 1, which then cancels with that one to just leave you everything else. So the degree of f of x, we're going to call it d. It has to be less than p minus 1 because the p minus 1 terms are canceling. All right, so then we're going to be able to use Lagrange's theorem here, right? So if a is equal to either all the way 1 to p minus 1, then we know that 1 is congruent to, we know that 1 minus a to the p minus 1 is congruent to 0 by Fermat's little theorem. So f of a is congruent to 0 mod p. Thus, f of x has p minus 1, which is more than d, roots mod p, right, because it has all of those. Hence, by Lagrange's theorem, that must mean that all of the coefficients of f of x are divided by p. In particular, the p has to divide the constant coefficient, which is formed from 1 times 2 times p minus 1, right, and everything else in between, plus 1. So this plus 1 is congruent to 0 mod p, which is to say that p minus 1 factorial is congruent to minus 1 mod p. So that's it's an if and only if, right? So that's the forward direction of the proof. And then the other direction of the proof is here. Let me get my thing straight. If we have n minus 1 congruent to minus 1 mod n for some positive, n greater than 2, if m is any factor of n, then of course n minus 1 is congruent to minus 1 mod m. That goes back to the theorem from the start of the lecture. That's based on using that, yeah. And so if m is less than n, then that means that, well, if you think about it, if m is less than n, then that means m is a factor of n minus 1 factorial, which then means that n minus 1 factorial is congruent to 0 mod m. And so 0 is not congruent to minus 1, yeah? So that means that there cannot be a factor of n less than m. In other words, n only has the factors of itself and 1, which means that n is prime. So there you have it. That's Wilson's theorem. Now, finally, the part you've all been waiting for, some calculations. All right, so applications. Here we go. And by the way, so you notice that Lagrange's theorem wasn't really used for Fermat's little theorem. It was used in combination with Fermat's little theorem to prove Wilson's theorem. That's what happened here today. So anyway, just saying. That's why we had to cover Lagrange's theorem in this talk, so we could put them together to get Wilson's theorem. All right, so here's an application of Fermat's little theorem. Suppose you want to simplify 2 to the 50th mod 23. All right. In other words, 2 to the 50th is equal to x mod 23 for what x between 0 and 22. All right. Other people might say reduce 2 to the 50th into its least positive residue mod 23. All right. Anyway, 23 is prime. So we have 2 to the 23 minus 1, which is 22. 2 to the 22 is congruent to 1 mod 23, right? So 2 to the 50th is 2 to the 44 plus 6, which is 2 times 22. So this piece just goes to 1, and we're left with 2 to the 6th, which is 64. But mod 23, see, that's got 46 plus 18. So the 46 piece goes away because we're working mod 23, and we're just left with 18. So 2 to the 50th is congruent to 18 mod 23. And at this point in writing the notes for this lecture, I decided I'm going to start using the bracket notation because, yeah, sometimes it's just better. Let's see here. So simplify 3 to the 32. Well, in 11, z mod 11. So 11 is prime. So that means 3 to the 10th is equal to 1 in z11. So 3 to the 10th cubed is 3 to the 30th, which is 1 in z11. So I can write 3 to the 32nd as 3 to the 30 times 3 to the 2, which is 3 to the 30th times 3 to the 2, which is 1 times 9, which is 9. So now, do you need to know Fermat's little theorem to do these simplifications? I don't think so, right? But you can see how it could be labor saving, right? Definitely. Another example. Now this one is from Jones and Jones. This is their example 4.2 on page 69. But it's a good example. I think you'll find it in a lot of books. Sometimes this gets proved earlier in a different form using just divisibility. But anyway, here it is. So I'm gonna look at it this way. If x to the 25th is congruent to x mod 2, mod 3, and mod 5, right? Then we have that simultaneous solution of that set of congruences. Then it's also going to be true mod 2 times 3 times 5, which is 30, right? So then we'll have, you know, x to the 5th congruent to x mod 30, all right? Notice that if you want to look at it directly, 2 divides a, 3 divides a, 5 divides a implies 30 divides a. So, all right, anyway. So how can we prove that this, and this are true? All right, let's look at it. For p equal to 5, all right, p congruent to x mod 5. So in working mod 5, remember we have x to the p is equal to x for all x, right? And so that's an identity. So when we look at our x to the 25, we can look at it x to the 5 to the 5, which is x to the 5, which is x. So in fact, x to the 25th is congruent to x mod 5. So there you have it. There's the proof for 5. How about 3? Well, in mod 3, we have x cubed is congruent to x for all x in z3. Well, for all x, for all integers, which gives us the equation x cubed equals to x in z3. All right, anyway, so x to the 25 is equal to x to the 24 plus 1, which is x cubed to the 8th, all right, times x, which is congruent to x to the 8th, because x cubed is congruent to x to the 8th, all right, which then gives us x to the 9th, which is equal to x to the cubed, which is congruent to x cubed, which is congruent to x. So we get x to the 25th is congruent to x mod 3. Now, looking at it as a straight calculation in Z3, I put it in green. It's like x to the 25th is x cubed to the 8th times x, which is equal to this, which is equal to that, 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 which is so you notice the difference here is I'm working with sometimes equals, sometimes congruence, versus I'm just working with straight equality in Z3. Yeah. You can think of it either way. It's kind of up to you, but anyway, the long story short is that yes, x to the 5th is x to the 25th rather is equal to x in Z3, which is to say that x to the 25th is congruent to x mod 3. All right, same calculation up here. 25th, this 5 squared is 5 to the 5th rather, x to the 5th to the 5th, which is x to the 5th, which is the class with x to the 5th, which is that again using the corollary to the Fermat's little theorem. All right. Anyway, and then finally, x to the 25th is congruent to x mod 2. That's easy enough to prove. Just plug in 0 and 2 mod 2. You get, 0 is congruent to 0 and 1 is congruent to 1. So hooray! So there we go. We've proved it for 2, 3, and 5, which means we get it for 30, which is to say the following. x to the 25th minus x is divisible by 30 for every integer x, which is actually kind of like, whoa, interesting. But anyway, there we go. And finally, our last example for today, or for this lecture I should say, is to find all the solutions of the congruence x to the 42nd power, all right, plus 13x to the 26th power, plus 15x to the 17th power, plus 1, congruent to 0 mod 5. So, yes, in principle, we already have an easy way to solve this, right? We just plug in, what is 5 to the 42nd power? What's 5 to the 26th power? What's 5 to the 17th power? We could just, we could just plug in the 0, 1, 2, 3, and 4, or 0, plus or minus 1, and plus or minus 2, straight up into there and like work it out, right? But you notice we got the 42nd power and 26th power, and so it's a little bit like, I don't know, maybe I'm a little worried about the calculator quite dealing with it. Maybe it'll be fine, but I can easily make this the 420th power and the 2600th power and stuff like that. And the method I'm about to show you would still work, whereas the calculator probably will choke at some point if you just do direct calculation, right? But anyway, so here's how we do it. So we wish to find all the roots of this guy in Z5, but since 5 is prime, the corollary to the Fermat's little theorem tells us that x to the 5th is equal to x in Z5, right? So we can reduce the powers of x down, down, down. So like we have x to the 42nd, which is x to the 40th times x squared, x to the 25th times x, right? So that's x to the 5th to the 8th, x to the 5th to the 5th, right? In Z5, that just reduces down to x to the 5th times x, and x to the 8th times x squared, which gives us x to the 10th for the first piece. And, so I'm using this x to the 5th equals to x repeatedly to reduce the order, all right? Down, 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 until finally we get down to x squared plus 3x squared plus 1, which is 4x squared plus 1. So this x to the 42 plus 13x to the 26 plus 5x to the 17 plus 1 in Z5 is equal to 4x squared plus 1, right? This polynomial and that polynomial are equal in Z5. Or you could say that this and that are congruent mod 5, all right? But anyway, once you have this, then let's just plug in the classes, right? So you plug in 0 or plus or minus 1 or plus or minus 2, and you get yourself not 0, 0, and not 0. So there are two solutions, and you can see that also from the algebra that I do down here, right? So I found the two solutions by plugging in. Once I found those two solutions, I was like, oh, well, duh, of course I could factor a 4 out of change 4 to minus 4, factor the 4 out, I got 4 times x squared minus 1. So of course, x minus 1 times x plus 1 has solutions plus or minus 1. Surprise, surprise. I mean, no surprise. I don't know if I would have, like, seeing to make this algebra step, I saw that because of what I did in the green, okay? Not the other way around. And anyway, however you want to look at it, the solutions of the given congruence are x congruent to 1 and x congruent to 4 modulo 5. So you see this this corollary to the Fermat's little theorem, right? This one. Where'd I find it? Let me find it. I'll find it. This guy. Right, this one right here. This one is really nice because what it basically means is that when you're working over ZP, polynomials of order larger than the prime can always be reduced to polynomials less than the order of the prime. In other words, the theory of polynomials over Z mod P, it's really only up to order P that it's interesting. Everything, if you have order P plus 1, you can always like reduce it back. And so you can always collapse polynomials of arbitrarily high order in ZP back down to order less than P. So at least if you look at them as functions, I suppose if we look at them in terms of indeterminates, it's a little bit different. But hey, let me not get into all that right now. Yeah. Anyway, that's it for today, guys. I mean, for this lecture, I should say. Thanks.